Hello and welcome to the Chemistry Academy. In this video we're going to go over infrared spectroscopy in relation to the Advanced Higher Chemistry course. So infrared spectroscopy is one of the chemical analysis methods that you look at in Advanced Higher Chemistry, and it is probably one of the simpler ones to interpret out of all of them, but it doesn't really give you lots and lots of information. So in terms of when you're looking at infrared spectra, you kind of want to have an idea of what you're even going to be looking for to start with, and then just kind of seeing if it ties in with what you think you are looking for, kind of. So the things you need to know theory-wise though about the infrared spectroscopy is it is used to identify functional groups, so things like hydroxyls, carboxyls, amine groups, aromatic C to C, benzene rings, those sorts of things. That's what it will identify. So it's not going to be able to tell you about anything to do with any carbons bonded to other carbons, if it's just a regular carbon-to-carbon single bond, or things like that. So we're really looking at functional groups when we're looking at infrared spectroscopy. And the way that it works is that infrared light is shone onto or fired at some molecules, and that infrared light causes them to vibrate in certain ways. This is because of how the electrons are distributed among those the dipoles that are created in these functional groups. So like if you've got an oxygen bonded to a hydrogen, for example, in a hydroxyl group, there is an uneven distribution of electrons there, and that will interfere with infrared light. So basically all these types of bonds that have dipoles in them will absorb infrared light, and they'll absorb different wavelengths of that infrared light depending on the chemical environment that they have. So like I said, it measures the vibration, so quite often this will come up in your exam as well, is about which instrumental method involves vibrations of molecules, so that will always be infrared spectroscopy. And when we get the spectra out, and I'll show you some in a second, along the bottom axis, the x-axis, we have wave number. That's per centimetre, and the way the wave number is calculated is just 1 divided by the wavelength of light in the infrared region that's absorbed, but that wavelength is given in centimetres for this equation, which is why your wave number comes out as per centimetre. It may be the case that you get asked to calculate a wave number or calculate the wavelength of light from a wave number. It would just be 1 over whatever number you're given, but just remember that will be in centimetres or per centimetre. So your wavelength, if you were to work out the wavelength from a wave number, you would do 1 divided by the wave number, and that would give you out your wavelength in centimetres. If you were asked to calculate the wave number, as you can see from the equation here, you would just do 1 divided by the wavelength, but the wavelength has to be in centimetres. So a bit different to when we're looking at nanometers for the electrochemical spectrum calculations that we normally do, when we're usually looking at like the ultraviolet region and things like that. So just something to bear in mind when it comes to the units of the different wavelengths of light. So let's have a look at some spectra here. So we've got a couple, so I've just got a couple of simple molecules. We're just going to look at their spectra and how it relates to the information that you're given on page 15 of the data booklet. So the infrared spectroscopy wave numbers and absorptions are on page 15 of the databook. So we have a few columns here. I'm just going to touch on this because this is sometimes an issue that people have in their exams. In the middle, so for this second column here, we have the type of compound. So that's the type of molecule that you have. Then in the last column, you've got then what caused the infrared absorption. So that would be like what bond is actually causing that vibration that's been detected. And that gives you an indication of what the functional group is. So just be very careful when you're getting asked questions on infrared spectroscopy. Is the question asking you to state what type of molecule it is? If so, then you would put whatever is in the middle column. Or is it asking you what bond caused the absorption? If that's the case, you would just write what's in the last column. Or is it asking you what functional group does it indicate that's there? And then that requires you having a look at all the information and deciding what functional group that bond is going to be. So if it is, if you've got a C double bond O stretch, but it's in line with where the ester absorption would be, then that means you have an ester link as the functional group. If you've got a hydrogen bonded OH stretch and it's telling you then that the type of a compound is an alcohol or a phenol, then it means you've got a hydroxyl group is the functional group. So just be very careful of that and with the way the questions are worded, because that is something that trips people up a lot. So let's have a look at ethanol. So we know that ethanol has a hydroxyl group, so we would be expecting for there to be some absorption where there is a hydrogen bonded OH stretch. So as you can see, you've got the broad peak there around about that wave number. These wave numbers aren't always specific, so you will sometimes see them slightly off. So you can see here that the databook's telling us it should be a bit higher than that. It should be around about 3,600, but here it's around about 3,000. So you sometimes have to take the exact wave numbers with a pinch of salt. But if you do see like a broadish stretch, then that means that you've most likely got a hydroxyl group around about this area of the spectrum. If we look at here, we've got ethanoic acid. It's got although it's not a class as a hydroxyl group here, it is a carboxyl because it's the whole carboxyl group. It still has that hydrogen bonded OH stretch, and you can see that's a broad peak here as well. This region of the infrared spectrum down the far right side, that's known as the fingerprint region, which is quite a detailed region. You get a lot of different specific peaks that can be kind of used to more easily identify what your molecule is, and that's why it's known as the fingerprint region, because obviously if you think of people and crime investigation, we can identify specific people by their fingerprints, so that's why they've named that area the fingerprint region. It's not really probably something you'll get asked about much, but it's just quite good to generally know that that is known as the fingerprint region. It can look a bit busy in this area, so I would usually look for other peaks first, but yeah, it's still a useful bit to look at. So for ethanol, the only thing we would be looking for here is the OH stretch, because that's the only functional group really in it. For the ethanoic acid, it's a carboxyl, so as I've said already, we've got that broad OH stretch, but we would also be looking for a C double bond O stretch, and it would be one for a carboxylic acid. So if we look down, that should be a peak at 1,725 to 1,700, so there's not really a clear scale, but that'll be about 1,500, so that'll be our C double bond O stretch there, which is a characteristic for if you've got a C double bond O stretch in a carboxylic acid. Therefore, if you were asked for what functional group there would be, because it's a carboxylic acid, you'd be expecting it to be a carboxyl group. So this is the sorts of things you're looking at in the IR spectrum, is just what functional groups is it showing that are there, and does it tie in with what I'm expecting. So if we look at the ethyl ethanoate, the ester here, so we would be looking for, because we know it's an ester, we'd be looking for the ester, just a regular ester, C double bond O stretch. So we can see that is here. This peak here, that's just for the C to H bonds that are in the alkane chain for this. Then if we go down and look at this diethyl ether, so that's ethoxyethane, we know it's an ether from the name, so we'd be looking at the alkyl ether stretch. That's what we'd be looking for, and we can see that here. Okay, now when you are giving IR spectra in your exam, for most of the questions you will be given you'll have worked out an empirical formula, and you'll know what the molecular formula of the thing is, so you kind of have an idea of what functional groups you can maybe expect. So for example, if there's 2 oxygens in the molecule, you'd be expecting either it to be like a diol, so there to be 2 hydroxyl groups, or you'd expect an ester link or a carboxyl group, because they're the types of molecules that we would expect to have 2 oxygens in them. If you had the molecular formula and you know it's got nitrogen in it, then you maybe be looking for a nitrile or an amine group, something that's got an N in it. If you had a molecule that only had 1 oxygen atom in it, you'd be either looking for it to be an ether or an alcohol. So you'd be looking for the CO ether, alkyl ether stretch, or even the aromatic ether stretch, and the CO, or the OH, sorry, hydroxyl group stretch. Okay, so It's a good idea to have an idea of what types of molecules maybe you are looking for. So like I said, normally you will have a molecular formula or something to go with. But that's how you kind of want to do it. Have a look at what major peaks you've got, what functional groups do they relate to, and then that can help you whittle down what your molecule is or what type of molecule you've got. Just to finish off, it's just one of these multiple choice questions from one of the past exams. I think it's from the 2018 Advanced Higher paper. So you're given this molecule here and asked what absorption you wouldn't expect to get from an infrared spectrum of this molecule. So again, what we want to do is look at what functional groups we've got, so we can then see what absorption we're expecting. So I don't know why that was so hard for me to get out. So the functional groups we've got a C double bond C, so an alkene. It's just a regular alkene. So we would then probably be expecting this stretch here. We've then also got this single wee oxygen here. In fact, I'll make this a different colour. That's a single bonded oxygen in the middle of a carbon chain, so that is actually an ether. However, it is attached to an aromatic, it's close to an aromatic ring, but that one itself is actually an alkyl ether because it's not within the aromatic ring. So again, we would be expecting that one. And then the last functional group we've got here is the hydroxyl group. So that would again be giving us this hydrogen bonded OH stretch, which means we would be expecting a stretch at 3,600 to 3,200. So far we've ruled out A and D. So what we need to do now is look at what the other wave numbers we have left and see what they tie in with. So we've got 2,962-ish, so that's an alkane for CH stretches. So we do have alkane CH stretches, so we would probably expect that, but we'll just double check the other one. So the other one is for an aromatic ester, and yeah, we don't have an ester here at all, so it's not going to be that one. So C is our answer, because for B we have got CH alkane stretches. So hopefully that helped you a little bit with infrared spectroscopy. It can be a bit of back and forth with these chemical analysis things. You think you've worked out what you've got, but actually then something doesn't really make sense. So it is, like I said, a good idea to have a rough idea of what you might be expecting in your infrared spectra before you have a go and look at them. And like I say, in these questions in the exam you get where you're trying to piece all these bits of information together, you will usually have a molecular formula to go off, so you can kind of work out from that what functional groups you'd be expecting to see. If you did find this video useful, please give it a like. Don't forget to subscribe, and I will see you again soon.